So now we can focus on the problem of finding bridges. So the challenge obviously here is that we want to find a bridge between the left half and the right half without actually computing the upper holes. Because if I compute the upper holes, then we know how to do this in log squared time. We saw this next week. Now the question is, how do we do this without knowing what the upper hole is? This is very challenging, and in fact I don't think without any prior background you can actually solve this. Since we saw in the last videos or in the previous week's videos that there is no common rule about what is the upper tangent. You cannot come up with rules such as the common tangent is between the points with maximum y coordinate or things like that. The common tangent could be between any 2 points when we just focus on the left half or the right half. So we have to do something quite ingenious. And the idea here is the following. First of all, we observe that finding a common tangent is equivalent to finding a line, because we can just say, instead of finding the common tangent or this line segment, we can just find the line that goes through it. Okay, so finding a bridge is equivalent to finding a line, but this line should have two important properties. One of them is that it should pass above all the points, but this is obvious because the tangent to the left and the right half passes above all the points. But it also needs to have another property, because I can come up with lots of purple lines like these that pass above all the points and up, but obviously none of them is the common tangent. The second important property is this one, that it should have the lowest intersection point with the separating line, with this dashed line. Why is this? So why does this property need to hold? Let me explain this. So finding common tangent is actually equivalent to the following problem. Imagine that this is the convex hull of the point set of the input points, okay? And then I have this dashed line that is at the median x coordinate. When I look at this picture, this edge is the common tangent between left and the right. And in fact, what the main property of this edge is that when I go downwards, is the following, that if I start traveling from plus infinity all the way down, it is the first edge of the convex hull that I visit, right? So when I'm going down, this is the first edge that I hit, and that's the common tangent. Okay, so that's the edge that I want to find. And now the claim is that this edge has these two properties. One way to see this is the following, that points that are inside the convex hull cannot be separated from the remaining points with a line. So if you have a convex hull like this, any line that passes through this point will have some of the points to one side and the other points to the other side. Whereas if you have a point that is outside, let's say above the upper hull, you can find a line that goes through this point such that all the points are below. In other words, if you have a point and if you have a line such that all the points are below this line, then this is a proof that this point that I pick is outside the convex hull. By finding the lowest point that has these two properties, I'm finding a point where a transition happens from being outside to inside. In other words, when I'm moving downwards along this vertical line, for example, I'm stopping here, I can find a line such that all the points are below, so therefore I know this is out. I move a bit more down, again I can find the line that has all the points below, so this is also out. At some point I cannot find the line that goes through this point and has all the points below it, so therefore this is inside. At some point a transition between being outside and being inside happens, and that transition point happens at the point that has the lowest, that is the lowest point with these two properties, or with this property. Okay, so therefore a line that satisfies both of these properties is a line that has this edge of the convex hull that I hit when I go downwards like this. Okay. If you have understood this explanation, then you can convince yourself that finding a bridge is equivalent to finding a line that has these two properties. And now the rest is easy, because we just need to translate this mathematically. finding a line that can be said to be equivalent to finding a and b, because once I find the values of a and b, then I could just write the line as y equals ax plus b. So this sentence can be translated as finding a and b. It's the same. What about the condition 1? How can we translate this? Well, mathematically speaking, this condition 1 is equivalent to this condition, right? If I plug in the value x and y of the input points, then yi should be less than or equal axi plus b. In other words, it means that the y coordinate of a point xi, yi should be below this y coordinate. So that y coordinate is axi plus bi, sorry, plus b. Okay, so that condition is easy. What about the second condition? Well, the second condition is also easy. Imagine that this coordinate is xm of this vertical line, that the coordinate of that point is going to be xm comma axm plus b. We want to find the lowest, which means that we want to find the smallest value of y coordinate. So we want to minimize this. So we want to minimize this expression while maintaining all these inequalities. This is an instance of linear programming or linear program, and we're going to look at this in the next video.